Synthetic data is becoming central to how financial institutions and regulators analyze risk without exposing sensitive information. In our last article, Synthetic Data in Financial Services, Reshaping Risk, we showed why this matters. In this video, we'll go a step further. I'll walk you through a step-by-step how to generate, validate, and assess synthetic financial data using World Bank indicators in Python. Along the way, we'll test both analytical fidelity and privacy. By the end, you'll not only see how the code works, but also how to present results in a way regulators and managers can actually use them. I'll quickly walk you through some of the indicators that we've chosen here and the reasons that we've chosen them. What I've done is I've gone to the Atlanta Fed and looked at the indicators that they've used for their nowcasting of GDP. And they have consumer spending, non-residential fixed investment, residential investment, inventory investment, net exports, and government spending. So we've tried to accommodate some of these different factors into our GDP forecast, which we'll use to test the analytical fidelity throughout the synthetic data series. Next, we've chosen a panel of different countries to look at. The first 7 fit into the G7, the next 4 fit into what's called the BRICS, and 2 are another added in, so we have an even split between emerging economies and developed economies. Now, to save some time, I've already gone ahead and set up all our initial data pulling and configuration to get our feature set that we want to use. This is all available in the GitLab repo, and you can take a look and run through the IPython notebook, or the Jupyter notebook rather, yourself. Here we're just loading that in, and we're checking to see that it's loaded properly. We then use the WD data library, which is a convenient library that queries the API to get the data. All we have to do is pass our indicators in our countries, and we get a nice data frame out of that with our start date and end date. So we've gone ahead and done that, and you can see here, this is the initial kind of view from pulling that data. Now we have to clean the data a little bit and calculate some additional columns. Now we have to clean the data a little bit and apply some transformations to a few of the columns so that we get everything on a comparable basis. We want to look at things in terms of percent of GDP or percentage growth. And we're going to convert the columns that are in local currency units and also constant values into percentage GDP or year-over-year percentage change. So you can see here we've gone apart and we've done this. We have a couple helper functions just to get the percentage of GDP. And we also have the year-over-year growth helper function. For inventories, we already have it in local currency units, and so we can just divide by the local currency units for GDP to get as a percent of GDP. But the rest of our figures are in USD, and so we need to divide by GDP in USD. And so that's kind of why we have both the GDP in local currency units and also the GDP in USD. Here we also calculate our net export columns rather than having imports and exports. We also have the net exports columns. And we append the columns to the data frame. And you can see this is the resulting data frame after calculating the new columns. From here, we want to generate our feature set, which is the set of features we want to take into the regression later on when we test the analytical fidelity. These are going to be our year-over-year percentage change and are also percentage of GDP columns as we've discussed. And this is the output of our final panel data set. Again, for the regression, we're only going to take these features, but it's good to have all the data in case we need it and when we look at the kind of privacy and going back. Now that we've generated our features, really quickly, you can see the data set that we've created, the panel data set we've created on the bottom here. Just do some quick exploratory data analysis just to show you what's going on here. So we've imported matplotlib, we've imported Seaborn, and we've put together some figures, some simple scatter plot and correlation panel, as well as a histogram. So you can see the distributions before and after we create our synthetic data set. A quick ANOVA table to kind of see the max and min values and where our kind of median observation line lies and also how many we have. And as you can see, we dropped the rows for the empty ones. So we have 319 observations total. You can get an idea of some of the distributions here. You can see from the correlation matrix here that the strongest correlations are between labor factor productivity and gross fixed capital formation, as well as personal consumption expenditure and gross fixed capital formation. If you're following along at this point, make sure you've already set up your Python environment and have the required libraries installed. As I've said, we're going to use the SDV library for this, which I've already gone ahead and installed previously. For this next part, we're going to generate our synthetic data set. We're going to use the SDV library to do so. It's much more simple to implement, especially when you're testing and you're trying different models to see what works. With synthetic data, it's a bit of trial and error. You want to test different models, you want to run different configurations, you want to see what works the best for you to get the best balance between analytical fidelity and privacy preservation. The steps for this first part are fairly simple. We're going to follow the recommendations from the FCA that you should always apply domain constraints to your financial data set. This ensures that you don't get severe outliers, especially when oversampling and creating many more rows than the actual data set contains. You get some edge cases where values end up being higher than those constraints that were initially put in place. And so we want to make sure we actually capture that and make sure that there aren't values outside those ranges. For our first test of creating synthetic data, we're going to use the Gaussian Copula method. And this transforms each variable into a standard normal and then takes the multivariate normal of those transformed variables, capturing the joint distribution, and samples from that joint Gaussian, as it's called, transforming the values back to their marginal distributions. Basically here we get a synthetic data set that helps capture those pairwise correlations between our features. One of the downsides with this methodology is that it tends to smooth out the tails, and you don't get those extreme outliers that may exist or those tail risks and extreme events, which can be important to capture in some data, especially when assessing risk or looking for events that might be low probability, but extremely impactful when looking at it from a systemic point of view. You can see this in the tutorial that we posted on the blog. It's pretty evident when we compare the synthetic data set with the real data set, how this happens. And you can see, like, if you're looking at unemployment or foreign direct investment here, we have a lot more values in the real data set that are outside that kind of 3rd to 4th standard deviation range, whereas our synthetic data set, it has kind of clipped those tails. And it's something to be mindful of when you're considering different approaches to creating synthetic data, that the Gaussian copula is great for preserving realistic correlations in the overall distributional shapes. However, it may underrepresent extreme events, and something like a GAN or a heavier tailed model might be better if you're trying to predict and forecast the probability of extreme events occurring. Now that we have our metadata, we're going to apply the domain constraints. And there's a couple of ways we can go about applying the domain constraints with the SDV library. You could import constraints specifically and apply them to specific columns. So if we imported fixed increments, let's say, we would apply fixed increments as, let's say, constraints equals fixed increments, column name equals year, increment value equals 1. So that our year column only ever increases by 1. We could also import fixed combinations. For this to work, we would do something like fixed combinations, column names equals country and year. This way we only get the same combinations that already exist in our normal data set. Cannot assign to a function call, oops, missing this. Between column and year. However, we'd have to change the year column to be categorical, whereas we've assigned it as numerical. We're going to do neither of these. We're going to do from SDV.sampling import condition. And what this is going to allow us to do is sample on our features and can pass through the conditions between our country and year variables that already exist in the data. Now we're also going to set some bounds here. So I've already preset these bounds and pre-configured them. What these bounds are going to do is after we generate our synthetic data, we're going to ensure that none of the values are outside of these ranges. And we're going to clip them if they are. So first, we're going to do our constrained columns. Calls equals panel. Country. I cannot type today. Copy. And then we're going to pass these constraints through columns when we generate our synthetic data. So now the fun part. Now we get to generate our synthetic data set with the Gaussian Copula method. So we're going to initiate our synthesizer. We're going to pass through the metadata. And we're going to also add in some constraints, some domain constraints here when we directly set up the synthesizer. So what we're going to do is we're going to enforce min and max values so that the maximum and minimum values are aligned with the real data set that we're passing. And that'll be similar to what we had seen back here. This just ensures that it doesn't generate any values outside those minimum maximum ranges. You might not want to turn this on depending on your data set if your bounds are actually outside that. If you calculated bounds that are outside of that, you want to make sure that this is off. Another thing we could pass through here is enforce rounding. Now, when we generated our percentages, we didn't actually round the values. But let's say we had rounded the values to 2 decimal places. Then this was ensure that the synthetic data that is created ensures that all the data is created is rounded to 2 decimal places. We don't need this because we didn't do that, but we will keep the enforce min and max. And now we are going to fit it with our country, year, and features. And then when we sample the data, we're going to be sampling from remaining columns. And we're going to pass through those constrained columns as those known columns so that we keep them in our as intended in our output of our data set. And I'll just show you the result here. And it'll take a second or here to generate. Have a sip of coffee while we're waiting. You can see it's going through all the rows of data in the remaining columns. And this looks pretty good. It maintains our year and country. And if we just do length, well, we'll add a length df-synth. You can see it's maintained our number of rows exactly. Now that we have our synthetic data set, let's go ahead and run those same tests that we did for our real data set just to get a bit of a comparison here. So we'll copy this from the exploratory data analysis section. We'll paste it down here. Instead of our panel, we'll pass through our synth data, features.describe. We don't need to do that because we just did this actually above. Don't need the ANOVA table, df-synth. And that looks pretty good. Oops, we want to call this synthetic data. And what we can do is we can overlay the histograms from the original data set so that we can get a side-by-side comparison just as a quick check. What I've done is I've just gone and copied the code from the tutorial on the blog. And we're going to paste that in here and modify it a little bit. So I'll highlight this out. Features. Synth. Calls. Looks good. Real synthetic. We don't need this. Actually, we do need that. So you can see we get our original histogram, heat map, which is still there. No, histogram. I don't know why I hid the heat map. Didn't mean to do that. Yeah, it's gone from there. And we can see our correlations overlaid here. Now, this might be a bit of a problem. Our net exports are all clipped at 0. And I have to go back and see, did we clip them at 0? We did. So we don't actually want to do that. But why would they be 0? No, net exports can be negative. We also don't want them yet 150. Let's just make them all negative 80. Okay, good. Now that we've set the bounds to -80, we're getting bounds back in normal ranges. That's my mistake there. Let's take a look at the correlations for PCE. So between inventories, yeah, I think that's pretty close to what we had before. If we scroll back up here, 0.49 between inventories. 0.48, yeah, so I mean, the correlations seem good. So while our figures are clearly not accurate, like the distribution is the same, the range is just significantly less. And it's because of how it's sampled from this, right? Like if you look at the distribution, it looks relatively similar. However, obviously the range has changed quite a bit. This actually might impact the regression that we run, because we no longer have these large positive and negative values of consumption, which would significantly impact GDP. Now that I think of it, do I have to rerun this whole thing? Oh my god, I didn't include GDP in here. Okay, slight oversight. I realized when I'm thinking about the regression that we didn't actually include GDP in our features. Going to be important. We're going to need that. And so what we're going to do is we're going to add in, if we go back to World Bank data frame, we need to add in GDP USD. And it's going to be year over year. That should be good. And once we add that back in, yeah, so we get our GDP USD year over year. We can calculate our features. That looks good. Let's make sure we have GDP here. We do. Exploratory data analysis. This should all be good. And now this is in our features, so we don't have to change much more. We just had to add 2 things. We'll have to rerun everything. But I just want to make sure that 50-50, I guess, makes sense. We did 50-50 with everything else. Let's go back here and redo this. I'm pre-training myself. Every time I train the synthetic data, I take a sip of coffee. And like I said in the beginning, creating synthetic data sets is a lot of trial and error. And so you're going to notice things in your data when you're going through this and thinking, oh, maybe I should adjust that. And that's completely normal and good practice. You should be looking for things and looking for ways that you can better your data set. All right, we've gone and implemented extreme gradient boosting. We've also implemented cross-validation with 5 k-folds. And this is important because if we just run it once, we're only using a subset of the data to actually test on. And that subset of the data could be very specific to one particular country. So it's important to run it across a few different iterations where we're using every data point for both testing and training. This gives us a little bit more reliable testing figures between the two models and also the data set to see across multiple iterations how the synthetic data performs compared to the real data. Code will be posted in the repository. I'm not going to go through it because it's a video for another day, and let me know if you do want to see a video on fold cross-validation or XGBoost, extreme gradient boosting, and we can look at some regressions in that regard specifically to the data. You can see what it outputs here, and so when we test our real and synthetic data, we get an output of some scores here. So R squared, root mean squared error, mean absolute error, and the standard deviations as well. And then we can see a little bit of the difference between the real and the synthetic. Now, the standard deviation in the synthetic data set is going to be a little bit smaller. And that's because of how we've seen the distributions even out a little bit. So that's kind of expected to see that these deviations are going to be less than, the standard deviation is going to be less than what we see in the real data set. However, if we look at the R squared, it's fairly similar, around 0.3. So 0.35 in the synthetic, 0.31 in the real data set. Not highly explanatory, but that's also expected. I mean, forecasting GDP is not as simple as looking at the year-over-year percentages, especially with the small data set that we have. You really wanted to look at the inputs specifically on a more specific time frame rather than yearly. Looking at the features, we can see overall that they're actually fairly consistent. The biggest difference we see is in the gross fixed capital formation of 0.11. And it's not too far off, though our synthetic data is a little bit higher. But it appears that everything is fairly accurate. And we can tell by the Pearson correlation between these features that it is indeed fairly accurate. We get a score of 0.92. So anything about 90% is pretty good. This is probably overfitted a little bit, but again, because we're using such a small data set, if I run this once, it doesn't look quite the same. And really, again, the importance here is not to validate the efficacy of the regression that we're running or the model that we have. This would take iterations and iterations to get good. We'd need a better data set. But it's to assess the difference between the real and synthetic data for its actual usefulness. And this is more of what we want to see, because we want to see, okay, do the correlations hold? Does the assessment of the individual variables lead to a similar assessment across the real and synthetic data? And this proves that it's pretty close. Like I said, a gross fixed capital formation is a little bit higher than synthetic data, and then we get personal consumption and exports a little bit lower than the real data set. And likely attributed to the distributions themselves when we use the multivariate Gaussian, which we could adjust for in some sense with some of those parameters by specifically applying a different distribution, and that might be something to play with. But for this test overall, it seems like it does pass. The R squared difference is less than 0.05. The root mean squared error difference is less than 10%. And the feature importance correlation, or the Pearson correlation between the features, is greater than 0.9. So say that the fidelity of it is pretty good. Okay, now there's two things we can do to improve the privacy of our data set. The first is adding some noise to the data while maintaining the analytical fidelity. So we add an even amount of noise to each record to make it indistinguishable individually, but still maintain and preserve those correlations and the analytical fidelity of the individual data points. Well, overall, in terms of how we're doing our analysis. The second is to check the rows and how specific the identifiers are for individual columns. So let's say you had name, age, income, and you needed to check how identifiable individual rows are. And usually you set some sort of parameter where they shouldn't be less than 3 rows that are individually identifiable, so called k-anonymity. And it ensures that each unique combination of those identifiers appears at least k times in the data set. And if not, then we can add some privacy preservation to that to be able to anonymize the data a little bit better so you cannot identify any individual or single row. Now with our data set, we don't have that level of sensitivity, and there's no real benefit to doing k-anonymity checks or adding any kind of groupings. It would actually take away from the analytical fidelity in our data set. So we're not going to do that. So number 2 here, we're just going to cross out. And I've created a simple function here called privacy wrapper. There's a level of detail here in terms of how sensitive your data set. And so the Financial Conduct Authority, or the Security Supervisor in the UK, they suggest that for very sensitive data, you should be using a very low level of epsilon. And that's because it adds a lot of noise to the data and makes it very private. However, for our data set, it's not very sensitive, and we can get away with adding a little bit of noise while reducing the privacy of the data to preserve some of that analytical fidelity, because it's a trade-off. The more noise you add, the less fidelity you're going to get out of it, or the less usefulness you might get out of the data, because you're now changing the data set quite a bit more. And the sensitivity also impacts that as well. You tweak the sensitivity parameter to adjust how much one record can change the result in itself. We also add a random state as we had previously for our regressions to use that seed for producibility, reproducibility.
1 minute, 37 seconds later.
With our function here, we're actually going to pass an epsilon of 5. It's not quite as privacy preserving, but allows us to maintain some more analytical fidelity, which we'll test later. You can see we print out our original data set just a little bit to get an idea of what's changing here. And if we scroll down, once we add in and we pass the data to the privacy wrapper, you can see it's added some noise to the data, so it's slightly different. Just looking at Brazil for 2001, PC is 3.198, whereas PC is 3.040. So what we'll do next here quickly is I'll just show you, we'll compare the fidelity between the synthetic data set that we originally created and now the updated one with the noise added to it. We'll do the same thing. We'll get our real metrics and our synthetic metrics, but we'll call them priv metrics and synthetic metrics, and we'll pass through df priv features and df synth features UCV. Go back up here. We'll assign this. Oh, forgot to pass through. Assume our real data is our private data here. So you can see it's very similar. The correlations are very similar. Maybe even closer to the real data set. If we actually pass through df priv here, and we do df real, because that's what we want to compare with, is we want to compare our panel with our actually private data now to ensure that the fidelity is still held. And you can see we get a good check mark here. Our feature correlation is a little bit lower than what we had in our synthetic data set, which is expected to some extent because we've added the noise. But the R-squared difference is good, and the root mean squared error difference is good. So overall, I would say it maintains the analytical fidelity, adding the noise to the data set, while increasing the privacy preservation of it. It's important to test and compare the different models so that empirically we find the best model for our data set through trial and error. As I mentioned in the beginning, you might try one model and go through and find it doesn't work very well, and you might have to tweak some of the parameters to get the best fit. Well, this kind of helps you go through a bunch of different models and see which model out of the gate fits best for you. While you still may need to tweak some parameters down the road, it gives you a good starting point. Now for our data set, the focus is on maintaining that correlation. So we're going to use the Pearson correlation as a comparison metric. We're also going to use a built-in quality report in the SDV library as a second kind of check and metric to compare. So we're going to follow similar steps to what we had done before, except for we're going to use multiple models this time. We're going to compare them. We're going to fit the model and train it on the real Panda data set to learn the statistical patterns and the correlations. We're going to generate our synthetic data using the same number of rows as the original data set and sample from the learned distribution. We're going to evaluate the quality using the SD metrics quality report, which I've outlined below, how it determines the quality of the data. We're going to save the outputs, and we're going to look at the evaluation to determine which model is the best. You can see here in this table, we've listed the models that we'll test. So Gaussian Copula that we tested initially, the CTGAN, it's a neural network, and the TVA, a variational autoencoder, also a deep learning model. Here's the parameters that we'll set for each model. We'll do a couple different CTGAN tests because in our initial testing in the blog post, CTGAN needs a couple different trials to actually get good analytical fidelity, whereas the first test that we did with CTGAN, it really didn't turn out very well, and the Gaussian Copula model turned out to be much better. While a neural network can capture better complex relationships, our data set might not actually take advantage of that, and really we just want to maintain those linear correlations between the two, those linear relationships. We've already imported the Gaussian Copula synthesizer. We'll now import the CTGAN synthesizer and the TVA synthesizer. We'll also go ahead and import the quality report from the SD metrics library. We'll set up some helper functions just to make our models. Now we want to run our quality report. Now we'll loop through our models and we'll do our testing and create our quality reports. Models. Oops. Model.fit. And now that we've run through our models and appended all the results, we'll put them all in a data frame and we'll organize the data frame to look at the best ones. We'll sort by the overall quality and the correlation. Okay, let's give this a run. We've had to make a couple slight modifications here in our code. Now we only want to do sample remaining columns with the fixed combinations on the Gaussian Copula, so we maintain those pairings. But because of how the neural network learns and samples from the model, we actually want to pass everything to it. And instead of constraining those columns, where we want to calculate sample the same number of rows, sorry. In addition to that, I realized our correlation gap is calculating for each feature, so we just want to take the mean and not get the p-values as well. We were getting some errors there. So when we run everything, it runs fairly quickly. We can see that we get fairly similar metrics to what we saw above with our Gaussian Copula, which is as we would expect. And the first run of CTGAN with 300 epochs and batch size of 512 doesn't perform quite as good, but the alt model performs quite well. So you can see the column shape score and the column pair trend score are about 85, 84, overall about 85. And then when we look at the correlation gap is quite small between the features. So what does this mean? Well, when you're trying to figure out which model is the best for your data, you want to evaluate whether you have primarily linear trends in your data, or if you have more complex, not linear trends, linear correlations, or more complex correlations that are more difficult to model, and therefore the neural network is able to model them a little bit better. And you can tell in our data, the neural networks actually do, or the machine learning actually does, and the neural network does a little bit better job at picking up those correlations between the different variables or features as they may be. So if we want to see do some graphing of the alternate version, we could also graph it against the Gaussian copula as we had done before. We've outputted CTGAN alt. Awesome. So we should be able to load these. Visualization, get visualization property. There we go. Perfect. And we can see our correlations here. And the similarity between the real and synthetic. And they look pretty good. They're all fairly close. Now we can do the same thing for the Gaussian, just to give you an idea of what the difference is. See, the column pair trends are actually higher for the Gaussian, but when we calculate the Pearson correlation between the two features, we got a little bit more disparity, a little bit higher. The last observation here, if we look at the visualization for the column shapes, we can see they are fairly similar overall. So an average score of 85, average score of 0.86, 0.85, 0.86. But if we look at some of the columns in particular, and we did notice this with the original Gaussian copula, that the PCE is quite different. And so it may need to make some adjustments individually, as we discussed before, for PCE, in terms of the distribution there. But otherwise, the CTGAN did a pretty good job of the distributions and maintaining similar shapes across each one. So it seems like, especially for PCE, so you can kind of tell when to choose what here, depending on what your data structure and what your columns look like. This is much better at mapping more complex distributions and more complex relationships, I should say, whereas Gaussian copula works very well for a few subset of more standardized distributions and converting them to a normal, standard normal distribution, or beta distribution as they default to. The final thing we'll do here is, now that we know CTGAN alternate performs quite well, we'll use that model and we'll run our exploratory data analysis and compare that with it. And the fidelity isn't quite as good here, actually. So although our model seemed to work out well up here, down here, it does not seem to have done as well. Yeah, you can see the R-squared is quite a bit lower than the real data set. When we run the cross-fold validation and the gradient boosting, extreme gradient boosting, we get the analytical fidelity is really poor here. And this was the observation we had with CTGAN in the initial trials. So although that we've gotten good results here, when we actually go and test the analytical fidelity, we're not getting great results. And if I go back here and I just see our Gaussian copula again, just for one final comparison, you can kind of see how you narrow down what to select and when to select it. So correlation in this sense, although the similarity of the data seems to be pretty close for CTGAN, when we actually run and test the data to do some fidelity testing, it doesn't perform quite as well. And we'll run this again. See, much higher feature importance correlation with the Gaussian Copula method. And yeah, our R squared is actually higher in the synthetic. Pretty good fit though, comparatively. I think if we adjusted PCE in terms of how the distribution is, we would get a really good result. But our fidelity assessment seems to work really well here. And the privacy is pretty good, privacy preservation, because we're not dealing with synthetic data. So in this situation, Gaussian Copula seems like the best method. And you'll have to play around with CTGAN and TVAE a little bit more to see if you can fine tune it to get a little bit better output. But I hope this helped visualize at least how you can compare the models and select which model works the best for you. We can help. Find links in the description for more information. Thanks for watching, and don't forget to like and subscribe.